So yesterday we encountered a question earlier in the notes where we had some directions that said determine whether an inverse function exists. And if it doesn't exist, like we just wrote, does not exist. So for instance, number 5, that was a parabola. And because the parabola would fail the horizontal line test, that means the inverse graph would fail the vertical line test and therefore is not considered a function. So that was neat. We just got to say doesn't exist and moved on. Unfortunately, that's not really the way it works in function land, is you can actually restrict the domain and then you're allowed to create an inverse function. So the last 2 questions on your homework assignment from yesterday, I think it's 57 and 58, they ask you to do exactly that. So they're going to start with a function that would not pass the horizontal line test. So like for instance, this guy. This is a parabola. Pretty boring parabola. It's the parent function. Looks like this. So yesterday, had I asked you the very first step of would it pass the horizontal line test, your answer was no. So then we would have stopped and said the inverse function doesn't exist. However, if we restrict the domain, meaning I only look at a portion of the parabola, then I would pass the horizontal line test. So can you identify a point that would be really nice to kind of like stop the parabola and therefore it would pass the horizontal line test? Yeah, 0 would be a great point to kind of cut it off essentially. So we're going to pretend that this part of the parabola doesn't even exist, and we're only going to look at this portion of the parabola. And there are other places we could have restricted the domain, but this is like the most logical place. So we're going to say our original function is x squared, but only for x's that are greater than or equal to 0. Yes, Dan?
You couldn't have restricted it further to the left.
Right, yeah. We'd have to either move to the right, or you could have restricted the whole right side off and gone to the left instead. That would have worked, yep. So because we're only looking at x's that are greater than or equal to 0, we're really only looking at this portion of the parabola. So think about the math now associated with finding the inverse. Remember, this is y equals x squared. So your first step in finding inverses would be to switch the x and y around. And then mathematically, we'd square root both sides. And this is where it becomes a little like you got to pay attention to what you're doing. A lot of kids go y equals, and then they're like little algebra robots, so they put down a plus or minus, because that's normally what we tell you to do, right? Plus or minus when you square root. And that is normally true, but it's not true in this case, because remember how I only took the positive half of the parabola? So I don't want the negative half of the inverse. So just the positive part of it. Very good. Again, you have a domain restriction, just like we did on the other ones. The domain is only for x's that are, 0 and greater. And that's the true domain for the inverse function as well. If you want to know what he looked like this. And that makes sense, even on an Abruzzo drawing. All right, so on 57 and 58, they give you a little bit of like freedom as to where you restrict the domain. I think I wrote a pretty clear note in my key of I restricted the domain here. So that way you can kind of tell what I was thinking. If you're not sure, a great way to start those questions is to graph them. They don't have to be anything beautiful. Just graph it on your calculator and sketch it out and decide where you'd like to restrict the domain. All right, so that finishes up the very important piece of that lesson. Could you now find your brand new packet? It's the big one. The first lesson is kind of a messy lesson, and we're reviewing some exponent properties and radical to rational exponent properties because we need them for an upcoming lesson. But while we're in the area of exponent properties, we decided to throw some other simplification things at you because these are things that show up on your SAT test quite a bit. And not only do they show up on your SAT test, these kind of questions show up on the no calculator part of your SAT test, because why not? So worksheet 1A, this is the notes side of the worksheet. If you guys flip over to 1B, that's the assignment for this. And you're only doing the evens on 1B. So write yourself a big note so you don't do extra work. You're just doing the evens on 1B. Alrighty. So a couple of properties that I need to remind you about back in Algebra 2. If you have a rational exponent, so a fraction exponent, it could be rewritten as a radical. So what they mean by that is x to the 1/2 power is the same thing as the square root of x. And we don't really think about this too often, guys, but there is technically a 2 in the index position of that radical. We just don't bother to write it. It's like how we never bother to write the first power on things. It's there, but we just don't write it. So similarly, what would be x to the 1/3? That would be the cube root of x. Now in this case, we do have to write the index. They're very important. But in both of these examples, it was raised to the first power, but it's not always the first power. What if it's like x to the 2/3 power? Well, that would be the cube root of x to the second power. And then a weird thing in math, the second power can technically be rewritten in or out of the radical. So it would be the same thing as saying the cube root of x, all of it raised to the second power. Isn't math beautiful? It is the same. Isn't that weird? Because it all reverts back to this rational exponent. Well, like, we can go through an example if you want. I would. Let's do one we're familiar with. So how about like the square root of 8 to the second power versus the square root of 8 to the second power like this. So square root of 8 is 2 square roots of 2, right? And if you were to square that, you would square the 2 and get a 4. And then when you square the square root, you get a 2. So you get 8.
Oh.
If you did the squared first, this becomes the square root of 64, which is also 8. So mathematically, the power versus the radical order doesn't matter because they're both powers. And like if you think about math and the order of operations is parentheses, exponents, multiply, divide, add. When you get into exponents and radicals are the same layer of order of operations. So it doesn't matter if you do one first or second. It's just like when you add 3 numbers together, you can add them in any order you want. Same idea. Okay? Thank you for that question. All right, so we're going to skip the warm-up just so we get through everything today. Oh, I was flashing through these a little fast. Do you guys remember these? These are called exponent properties. So these are things you're supposed to remember back from your days of algebra. If you multiply the bases together, remember how we're supposed to add the exponents together? And this property works in reverse. You can break them apart into separate multiplications, so keep that in mind. If you are trying to divide bases with exponents, you keep that base, but you subtract their exponents. Right here, if you have a power raised to another existing power, you multiply them together. This is my favorite property. If you have a negative exponent, that base is on the wrong side of the fraction bar, so you move it. It's a weird thing. This is a boring property. Anything to the first power, you just get back to it yourself again. And then everyone's favorite property, anything raised to the 0 power is equal to the number 1. Remember that property? That's the best one. So all those properties, because radicals are really exponents, all those properties work with radicals too. So we got to remember that. All right. But what if I give you something like from back in the day of Algebra 2 like this? So the first thing I'm going to ask you to do is rewrite this in radical form. So those of you who need a little refresher from algebra, you have your base, and it's being raised to the exponent divided by the index. That's how I remember this. So the rational exponent means 2 pieces of information. This is the exponent, the 7 is the exponent, and the 6 is what we call the index. That's the type of root that we're looking at. So this one is the 6th root of x to the 7th power. Unfortunately, this is not simplified because you can divide 7 by 6, right? How many times does 6 go into 7? Once, with a remainder of 1. Very good, 5th grade. Coming on strong. Do you guys remember doing those when you were little ones? Yeah, no one likes that. So what you guys just verbalized to me is actually the final answer to this. You guys told me that 7 divided by 6 is 1 with a remainder of 1. What does that look like for a radical? Well, I'm going to show you this a little differently. If we were to break up x to the 7th power in a way where I could partially reduce it and have a little bit left over, that would look like this. X to the 6th and x to the 1st. Why did I do it that way? Well, because of what y'all just told me. You told me 6 goes into 7 one time with a remainder of 1. Now the remainder is going to get stuck in the radical, right? Doesn't go anywhere. But how does this reduce, guys? 6th root of x to the 6th? That becomes x to the 1st power because you divide them. And that pops out of the radical. And then you guys remember the remainder stuck inside. So this becomes x times the 6th root of x. But my friends who could quickly say, oh, 7 divided by 6, that's 1 remainder 1. You could get to the final answer really quickly by doing that. And I know every Algebra 2 teacher teaches this one differently. Some of the Algebra 2 teachers have you guys write out like 7 x's. Like x, 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 x. And then you circle groups of 6. Because that's who escapes the jail, is like how the little kid teachers teach it. Okay. Some of you are like, I don't know what you're talking about. That's okay. It's weird. We teach square root jail when you're like in pre-algebra. Because that like resonates with middle schoolers apparently. The jail aspect of it. They're like, I can only escape the jail if I'm a twin. Like that's how square root jail works. But now that we know there's other types of radicals, that gets a little complicated. Alright, so here you have 4x to the 4/3 power. Notice the parentheses, the quantity is being raised to that power. So we have a cube root, and then you've got the quantity 4x being raised to the 4th power. So my friends who can tell me 4 divided by 3 is 1 remainder 1, maybe you already know what the answer is. That's awesome. My friends who aren't really sure what I'm talking about yet, we're going to break it down. And we're going to rewrite this 4th power. We're going to break it apart into 2 groups. 4x to the 3rd power with a leftover 4x to the 1st power. The reason I broke it up like that is because this is going to break down and this remainder piece is going to stay inside. So cube root of 4x to the 3rd power, that just means 4x is going to come out of the radical. It simplifies out. And then who's still stuck in the radical? 4x. Yep, you can say to the 1st power, but 4x. So back here, my friends who could figure out 1 remainder 1, this is the 1 remainder 1. This is what it looks like. Okay. Remember, our job in PreCalc is to like take things that were kind of procedural and try to make shortcuts because now we have a deeper understanding of it. Okay. So those are fun. And then I gotta throw this really weird rule at you, okay? If you have an even root taken to an even power and the result is an odd power, now you have to use absolute values on variables. Okie dokie. Let's talk about why. So let's create an example that kind of follows these parameters. If I have an even root, so let's say I have a square root. You don't have to put the 2 in the index, but I like to put the 2 there. And I apply that to an even power, so I'll say like x to the 6th. And the result, what would be 6 divided by 2? 3. And the result is an odd power. You cannot call this x to the 3rd power. You're supposed to call it the absolute value of x to the 3rd power. What? It's like they just made this up. Okay, now this does have a really, like, it makes sense once you start thinking about it, guys. If you had something raised to the 6th power, that would be an even number, right? Regardless of whether it was positive or negative. I'm sorry, not even. That would be a positive number, regardless of whether it started out positive or not. Like, for instance, if you took -2 and raised it to the 6th power, it's going to be a positive. But if you took 2 and raised it to the 6th power, it's also going to be positive. So regardless of what math you do to this, it's going to create a positive answer. And therefore, when you go to square root it, you're going to get like a normal number, like cool. But guys, if you took that -2 and raised it to the 3rd power, that would be negative. And according to like the laws of math, this is never negative. So to force your answers to be positive only, you have to throw absolute value bars around it. It actually has to do with the shape of a parabola, is like the really detailed explanation of it. For now, just know it's some weird rule in math. And the only reason I'm showing it to you guys is because it might pop up on your SAT. It does pop up on your book assignment you're doing for homework. My answer key has some like random absolute values. This is when they show up, when you have even root taken to an even power with an odd answer. You'll see absolute values around my variables, okay? I'm not going to test you on this. It might pop up in your, upcoming math series when you go to college. We just want to throw it at you just so you know where it came from, okay? But moving on. Yes?
For the last one, if you did an 8 instead of 6, wouldn't it come out to 4?
Yes, but that would be okay, right? Because that's not So the result has to be an odd power in order to need absolute values. So like I had to be careful what example I came up with to make sure it came out odd. So I could have done 10 square root, then it would have been odd. Okay? Because you're right. It's not like every time it's even, you need absolute values. Because an even power answer would always be positive. That's the difference. Good question. All right, guys, let's start simplifying this. So it's kind of your choice how you simplify it. Some kids like to distribute the 1/2 power. Some kids like to roll right into radical. I don't know about you. My brain does not think in fraction exponents very well. My brain thinks a lot better in radical. So I'm going to change this to the square root of 64 n to the 6. And this is a little easier for me to handle. So the square root of 64, better known as 8. So that simplifies out of the radical. And then the square root of n to the 6. Kind of. Kind of. Yeah, that's a stupid thing we just learned. Okie dokie. So look what... Yeah, we already have that. So we had an even root taken to an even power and got a resulting odd answer, which has to be forced to be positive. So we got to throw absolute values around the end of the third. So, well, 8's always positive. Only a variable would be me forcing it to be a certain sign. Good question. All right, the next one. Hey, good news. We have an odd root this time, so I don't have to worry about that stupid absolute value rule. So cube root of 8m to the 9th power. Now you can choose to do the power right now in the radical or leave it for out of the radical. I would like to leave it for out of the radical if you don't mind. It's actually easier for mental math if you save the powers to the end, usually. So this time, careful, I want a cube root this time. What's the cube root of 8? 2, good. And I do have a chart of squares, cubes, fourths, and fifths over there on the other desk. If you guys want it for reference, you can use it on your homework. You can't use it on tests, though. And obviously, you can't use it on your SAT test. Yeah. All right, so then here we have cube root of m to the 9th. That becomes m to the 3rd. But don't forget, this whole quantity is being squared. So now you're going to take the squared, and you're going to apply it to both the 2 and the m to the 3rd power. So 2 to the 2nd power, better known as 4. And then m to the, multiply these together, so m to the 6th. Very good. We didn't have to worry about absolute value on that one, though. Yes?
So when you're doing the absolute value
Mm-hmm.
on the other coefficient is negative, does the whole thing get absolute value?
Well, it would be a no answer if you had an even root on a negative coefficient.
Oh, wait, yeah, you're right.
That was a great question, though. That would be a really sneaky question on my part. I won't do that to you, I promise. Some other class, yeah. That would be really mean. Just throw like a complex answer out there and be like, whoop, there you go. Which we can take. You guys remember doing square roots with eyes? Like you can. It's not fun. It's not part of this chapter, so that's the good news. All right. So here's where I kind of mess with you again. Poor Algebra 2 kids. It's like we lie to you all the time. So these questions you did in Algebra 2. And you'd simplify them. And there are some rules in Algebra 2. Where you had to make sure you combined all of your coefficients and bases and everything was all combined up. It was beautiful. You can't have any negative exponents, remember that rule? And you can't have any existing parentheses because that means you have to distribute. So in Algebra 2, once you took care of those 3 things, you were like, oh, here's my answer, la-di-da. Okay, technically, in Honors Algebra 2, you did this. Technically, there's one more rule. You can have no fraction exponents in your denominator. Because think about this, guys. What is x to the 1/2 power? It's the square root of x, which someone out there in the math world decided one year that you can't have radicals in the denominator. I don't know. To this day, I do not know. I think it had to do with like back in old school math times where you had to rationalize it so you would be able to refer to a chart easier. They were all in the same form.
Oh,
but now it like, and actually Mrs. Gupta has told me that they really don't follow this rule anymore. But the SAT has not gotten on board with this yet. So they'll still make you rationalize it. Even though, like, the rest of the, like, higher math community is like, this is stupid. So, sorry, children. You're in a transition phase.
So there's no true actual reason why.
There must be. I mean, I don't think it's applicable anymore.
But an actual, like, mathematical reason to where you can't have a
yeah, it's not like it's wrong. It's just, like, the not common accepted notation. Yeah, it's stupid. It's like putting the first power. It's not wrong, but, like, no one wants to see you put a first power, because that's weird.
So you're totally not going to run like on the test, right?
Well, I'm not going to test you on this. Okay, then. All right. The SAT, however, if it was a multiple choice question, they wouldn't offer you a choice that had a radical in the denominator. They would make you rationalize it. So that it turns out like you might have the right answer sitting on your paper, but it doesn't match one of their choices. So you have to manipulate your answer to look like theirs or vice versa.
Dang.
It's annoying is what it is, right? So here we go. Number 5. Same rules as Algebra 2 with this extra rule here. And there's only one on their notes where we have to rationalize it. It's not horrible. It's actually pretty easy once you kind of look at it. So coefficients. Don't forget, coefficients, not exponents. So a lot of kids tell me the answer here is 5 because they're so excited about adding exponents. Guys, those are coefficients. So the coefficient is a 6. But speaking of adding exponents, remember what you do here with the x's to combine them together? You add their exponents. So this becomes x to the 3rd power. Oh, and now because you're pre-calc, I can do this to you. Don't use your calculator. And please add your exponents for your y's. So 4/3 plus -1/2. What do you need in order to add fractions together, 5th graders? Common denominators. So you'd hit this guy by a 2/2, and you'd hit this guy by a 3/3. And this problem becomes 8/6. I'm going to just call it minus 3/6, better known as 5/6. So this is y to the 5/6 power. And the rules from Algebra 2 stated everybody's combined, no parentheses, no negative exponents, and now no rational exponents in the denominator. This problem's done. Now the reason I made you suffer through the 5th grade problem in your brain or paper, remember what I said? Where do these problems show up on the SAT? The no calculator section of the test. So while I know it's been a while since we've forced you to get common denominators without a calculator, you can do it. If an 11-year-old can do it, so can you. That's my theory. Oh boy. Okay, so this next one, we got parentheses. So what are we supposed to do with this 3/2 power? Yeah, it gets distributed and therefore multiplied into the existing exponents. So again, without a calculator, I want you guys multiplying -2 times 3/2, and then also -2 times 2/3. So when you're multiplying fractions, you do not need to get common denominators. And if you're trying to save yourself a little brain energy, you can do some cross cancellation, they call it. So like here, the 2's would cross cancel. But not, oh, that's not the right problem. What is this? This is 2/3. Sorry, it's not even the right number. Okay, try again. Like I said, this is 2/3 times 3/2. Okay, so that one has lots of cross cancellation, right? It just becomes a 1. What does this one become? -3, very good. So this is x to the -3 times y to the 1st, but don't forget you still have the rest of this problem over here. And then that's not an okay answer for a couple of reasons. There's still combining you have to worry about, plus there's negative exponents, but we'll do the combining first. Combine those x's for me, combine the y's. What you got? X to the -1. And y to the -1, and then you're not done because a negative exponent means, yeah, they want you to move it to the other side of the, I believe it's called a vinculum. We looked that up one year. All right, so 1 over, you can say x to the 1st, y to the 1st, but normal humans just say xy. You're allowed to have those in the denominator because they don't have fraction-looking exponents, so that's okay. All right, I'm going to skip around because, oh, that one was a big X through it. That can't be good. Let's look at number 9. Any thoughts on number 9? There's a lot of stuff you can do to number 9, and there's no right or wrong answer as to where we start.
Distribute the -2 into every single
Good.
thingy.
Good explanation. -2 goes to every thingy. So we have x to the -4 over, let's see, don't forget this guy's an x to the 1st, so when I distribute the -2, as Cameron instructed me to all of them, x to the -2, y to the +4, and then x to the -5/2. Clearly not done. There's negatives all over the place. There's also some combining we can do. What would you guys like to do next?
Combine.
Combine down in the denominator?
Yep.
Okay, so with these being both multiplied together in the denominator, that means you're going to add your exponents together there. Careful here. You're going to get common denominators. So you'd have to multiply this guy by a 2/2. And that becomes -4/2 plus -5/2. So down in the denominator, you've got this y to the 4th still, but now you have x to the, what is that, negative 9 over 2? It is disgusting. All right. Here. About the 9 over 2? Here? Oh, here. Yes, there is. Sorry, I just didn't write that. Good catch. That would have been really bad in a minute. Because now what do I have to do with these exponents? Yes. And even when using a calculator, you'd be surprised how many kids still get this wrong. Because they're like very loosey-goosey with their negatives, apparently, like me. So negative 4 minus a negative 9/2. So again, you need common denominators. You'd have to hit this fraction by 2 over 2. And then do you guys mind if I call this negative minus thing a plus? Because that bothers me. So this is what? Negative 8/2 plus 9/2. What does this become? That's right, kids, 1/2. All right, so this exponent, which is from the x's right here that I subtracted. Oh man, I wrote this stupid. That answer goes in the numerator. When you apply this subtraction rule, whatever you get defaults to the numerator for now. And forever for now. And then don't forget, guys, there was still a y to the 4th power down in the denominator. That is the final answer. We're allowed to leave the y to the 4th power down there. Until we get to the next one. Then we're going to see something exciting. All right, so for the sake of time, I'm just going to like speed through simplifying this one with you guys, because I know you can add and subtract and multiply and do all sorts of things with exponents. Let's talk about adding these x's together. That would be x to the 7/2, y to the negative 1/2 over x to the 6. We would subtract these. And then aren't we going to move that y to the denominator at some point? Because there's some weird rule about moving negative exponents. All right, so 7/2 minus 6 would be like 7/2 minus 12/2, which gives you negative 5/2. So I'm just going to take the liberty of throwing this down to the denominator. You have x to the 5/2 and y to the 1/2. And then there's nothing left in the numerator, so a 1 up top. And in Algebra 2, they were like, beautiful. That's so good. And then in PreCalc, you're like, oh, we're not supposed to have this. So we're not done. Here's what we're going to do. We're going to take our work down here. And I'm going to kind of space it out a bit. I'm going to say x to the 5/2. But I'm going to multiply him by something. I'm going to call it the blue thing. But remember in math, if you randomly throw a factor into a denominator of a fraction, don't you also have to throw it up here? And we're going to do something similar with the y's. We have a y to the 1/2, and I'm going to multiply him by something. I'm going to call it the green thing. But again, if I do something to the denominator of a fraction, I have to do it up here as well. That's how I keep fractions balanced. All right, talk to me about the denominator. Your job is to give me a little more in the x's, so that way when I combine them, I no longer have a fraction. I'd like you to go as small as possible. And don't go negative, I should say that. So what if you combined it with an additional x to the 1/2? What would happen? Yeah, you get x to the 6/2, which Adam tells me is 3. Is that a fraction? Like, not the way it's written? No. So that'll work. But remember, if you do it to the denominator, you got to do it to the numerator as well. So using a similar idea, what could you combine? What additional y's could we use that'll kind of fill out the rest of the fraction? Another 1/2. Very good. This is hard for kids to think about because no one really enjoys fractions, but basically you're filling up the pie chart of the fraction. Okay, like 5/2 needs another half to get to the next full pie chart. I know you're like, pie charts. So the numerator, remember guys, the numerator can be ugly. I don't care about that. This is x to the 1/2, y to the 1/2. But look what beautiful thing just happened in the denominator. This becomes, Adam told me, x to the 3rd. And this is y to the, careful, y to the 1st. So just y. And then for some reason, math thinks this is a better answer than the previous answer.
Wow.
I know, right? Isn't it? Like, what a dumb rule. I don't know about you guys, but I don't think that looks simpler, but whatever. Whatever, math. do your thing. Okay, so you guys are going to work on 1B. And you're just going to do the evens, yes. In addition to that, oops, there we go. I'm going to post a PDF of this in a minute, but you have capital P, page 17. It's in that weird chapter 0 thing. There's just a few questions, and it's on this simplifying radicals business like we used to do in Algebra 2. So give it a whirl. These are examples from your book, which I think you guys will figure out. If you do have questions, though, please do come in. Like I said, guys, I'm not testing you on this like explicitly on a test. These are just topics that you need to be familiar with as you get ready for your SAT. But the radicals are important to us in an upcoming lesson. So going from rational exponent to radical form. Could you find the green sheet that you picked up? It's got a very ominous title. It's like Last Chance or something. I don't know.
Last chance.
Last Chance for transformations. I don't know. It's pretty cutthroat. I hope it's the last time we have to test transformations. Let's put it that way.
Are we testing it today?
No. That'd be really mean. That's like a pop quiz. That sounds horrible. So this worksheet's kind of neat. There is an answer key on the back to everything, by the way, so I'm not going to bother posting the key for you because you have it. And if you also notice on the back, we snuck in some extra factoring practice. So we want you to work on your factoring as well because factoring is going to come up real soon in our curriculum before we hit the section before 2. There's like a weird like intermediate section between 2.4 and 2.5, I think, where you guys got to be like little factoring wizards with me because we're going to do some rational operations where you got to multiply and divide and subtract and add fractions with factoring. Well, yeah, we don't want to confuse you. So the key's upside down. Right? What, you can't read that? All right. Yes. Yes. So this worksheet, there's this very funky looking little curve over here. And if you're me, you can't read anything. So the first thing you're going to do is you're going to kind of figure out where these points are. And I'm going to transform them like a point at a time because this is a weird little shape. So this guy is at -3, 0. So talk to me about the transformations that you guys see for f of -x plus 3. There's 2 transformations there. Anyone think they can identify them? And then we'll talk about order in a minute. But when I throw a -x into the function like this, what kind of a reflection is that? Yeah, over the y-axis. Very good. Reflection. Oops. Over the y-axis. Because it's going to negate your x's to the opposite. And then, I don't know why I can't write. And then what about a plus 3? Up 3. So I kind of already spilled the beans here, but if you reflect over the y-axis, that changes all of your x values. And if you move everything up 3, who does that change? Your y values. So these don't compete against each other, so it doesn't matter the order in which you apply these transformations. So if I took -3, 0, pretend it's right here, and then I reflected it over the y-axis. Now it's over here at 3, 0. And then I move everything up 3, and now we're at 3, 3. Oops, that's the wrong color. All right, so this blue point is up here now. And I'm going to do the same thing for each of the little like vertex-looking things on this shape, because this is a funky little shape. So this guy is what, -1, 2? So if I started at -1, 2, and I reflected it over the x-axis, sorry, the y-axis, and then I moved everything up 3, I think I land right there. And then, of course, I'll call this green, so why not? That's 1, 2. So if I reflect it and then move up 3, I'm right here. And then I'm kind of losing confidence because I don't think I'm going to be able to connect these dots very well. All right, let's call this next one another blue one. This is 2, -2. So if I'm at 2, -2, and I reflect it, and then I move up 3, I think I'm here. And then one more ordered pair, call it this red one. 1, 2, 3, 4, -2. So starting at cheapers, 1, 2, 3, 4, -2, if I reflect and then move up 3, I'm right here. And then this is where it all goes awry, because now I'm supposed to connect the dots and actually make it look right. So, You know what I need is bigger dots. Just need to make the dots really large and then it'll look good. I don't know, guys. It's not looking so hot. That's okay. I'm sure yours looks great. So let's talk about the I'm not going to do the next two for you, but let's talk about the transformations. There are two transformations I need you to describe for me on this next one. Talk to me about what this 2 does. Is it? Because it's in front of your function. It's what kind of a stretch? Yes, it's a vertical stretch of 2, which clearly will stretch the y's. And then what about x plus 1 inside of the function notation like that? Left 1. And if you move left, what direction is that changing? So once again, it doesn't matter the order in which you apply these transformations because they'll be the same transformation. All right, talk to me about the next 2 transformations. This one I think order does matter, so let's see if you can come up with the right order too. It's not a vertical compression, but a vertical... I'm using the wrong word, but I know what you're trying to say. What's this called? Reflection, yes. So you can call it a vertical reflection, or you can say it's a reflection over the x-axis, which does change your y values. And then what about a plus 2 off to the side? Up 2, which also changes your y values. So because both of these change your y values, you have to think about order. Guys, tell me which one happens first. The first one, because you said it in the right order, huh? I agree with you, Adam. All right, so the reflection over the x-axis has to happen first, and here's why, guys. If you told me the opposite of this, if you said, well, I'm going to move everything up 2 and then reflect it, what you're doing then is you're taking your function, you're moving everything up 2 first, and then if you come back and say, now I'm going to reflect it, look what happens to your math. What's going to change? Everything. This plus 2 all of a sudden becomes a minus 2, which is totally different from what you were interpreting it as. So this is not right, and I agree with your order, Adam. Thank you. All right, this question is kind of weird, these 2 questions. Don't worry about order so much on these because these are a little confusing. I just want you to realize that we don't always have to transform from the parent. We can transform from any old function. So like for instance, the original function was already starting at up 5. So when I look at this new function, I see 2 things that changed, basically. And that'd be this guy, and then this is different. So talk to me about this 2. What does that mean to you? Yeah, a vertical stretch of 2. Love it. And then originally we were already up 5, and now we're up 9. So what actually happened to this graph? Yeah, up 4 more. And this is where you can have a great debate about like, well, which order? Does it matter? Like, it does matter. I don't want you guys to hem and haw over this one, though, about order and who does what first and second. Because technically what we just wrote down is not in the right order, and it's not even correct if we do the right order. So don't worry about order on this section of the worksheet. Just tell me the changes that occurred from the beginning to the end. Take a look at this stuff. This is very much like what you're going to see on your test on Friday. So in order, this one does have to be in order, so be careful. Let's talk about this guy. So we're going to take our function of x squared, and the first thing I want you to do is shift it down 2. What does that look like? Oh, yes, I'll subtract 2 off to the side. Very good. Now I want you to reflect over the x-axis. What does that look like? Just like this? Ah, very good. Because the reflection happens after I already shifted down 2, you got to use parentheses. And now I want you to also vertical shrink 1/6, does that say? Okay, so I'm going to give myself a little more space. Again, it has to be out of the parentheses like this. Now, is that the only acceptable answer? Could you think of like some math simplification that would still be equivalent? Could we say, yeah, we could distribute it? I mean, I don't know why you want to, but you could. You could. You sure could. So either one of these functions, if we type them into y1 and y2, they're going to give you the same transformations, the same function back again. That's why these are kind of hard for kids, because order does matter. Let's talk about 12. That's what I'm worried about. Okay, got a square root. I want you to horizontally shrink. What does that look like? This is the weird one. Yeah, so it looks like this. Very good. And then I want you to shift everything up 3, which would be off to the side like this. And then I want you to come through and reflect over the x-axis. So because this is happening now, that reflection looks like this. Gross. This order of stuff, it goes along with order of operations. I think that's why it's, some kids, once they get it, they're like, oh, it's just order of operations. All right, now, the other functions at the bottom there, they're a little hard to see the graphs, so like I empathize with you on that one. But they're very specific about how many transformations. Okay, this one, you need to be able to get your transformations described in only 2 of them. But on these, you should be able to use 3 transformations. So talk to me about comparing, this is the original, right, to this new one that I highlighted in blue. Do you see any sort of stretching or shrinking happening to that one? Does it look any taller or x-intercepts pulled in? Not at all. So there's no stretching, no shrinking. Do you see a reflection? Yes, but over which axes? Good, over the y-axis. What does that look like? Good, that's inside the function, so f of negative x. And then apparently there's another transformation. So now I'm looking at my peaks and valleys, basically. This guy was as low as -1, and all of a sudden he's at 0. So it must have moved up 1. How is that going to look? +1, very nice. This is a lot harder than what I think you're going to see on your test. Your test is a matching question, kind of like on the last test, but this one has like, you got to match 3 of them. It's harder for you guys to develop the function notation without any like help. So if you can get these right, then you're sitting good for the next test. So try the next 2. Spoiler alert, I'm seeing some stretches. What kind of stretches are you seeing on the next 2? Vertical stretching, yeah. I don't feel like it horizontally expanded or shrunk at all, but definitely a vertical expansion on both of them. And it might help you. Like, I realize you guys are probably just going to peek at the key. I get it. But it might help you, for those of you who aren't going to cheat, to find a point and try to follow where it ended up. Like, oh, it went left so many units, or whatever ended up happening to it. Okay? I think you got some reflections on that one as well. Have fun with that. And if you're struggling on the factoring, let that just kind of be a warning to you. Like, okay, I am still struggling on factoring. Just come in and see me, guys. And if you can at least narrow it down to like what kind of factoring you're struggling on, that would be helpful. All right, your homework. You got quite a bit of it. Finish up this last chance worksheet. You got that tiny book assignment from page 17, and then you're going to do 1B evens only.